guys, welcome back to my channel, and today what we'll be doing is we'll be solving these math problems right here. Okay, so first what you might notice is that all of these are just figures, so I couldn't type down the question, so let me just tell you the question. So basically you can see these 6 circles here, and you can see that there's a specific part shaded using a different color, which you can see in a bright shade. So now what you have to do is you have to find the area which is shaded in each circle as the fraction of the whole area of the circle. So first I'm going to give you time to think of it, so you can pause the video and think about all of these 6 figures for a while. I know it might take a bit long because there are 6 problems here, and each of these are going to get harder and harder as we move on. And I think, in my opinion, this will be the longest video I have ever recorded in my life. So let's get a head start and solve our first problem. This one. Okay, so, whoa, yikes. This problem looks like huge confusing. So what can we do here exactly? So observe this with our eye level, what we might understand is that this line right here, let me just highlight it for you. This line right here is the diameter of the circle, I think. So I forgot to tell you one detail of all these 6 figures. So in each of these circles, there are 12 points which are lying around the circle. So basically, the distance between any 2 nearby neighboring points have equal distance. If we take any possibility, it's still the same. So for an example, if we take these 2 points right here, if you assume their distance is x, the distance between this point and this point is also x. This point to this point is also x. So using that clue, we can find the fractions of shading very easily. So let's just do it without chit-chat. So basically, the very first thing I'm going to do is I'm going to guarantee you guys that this point to this point is the diameter of the circle, and let me show you why I'm saying that statement. So basically, we know that the distance between any 2 neighboring points in this circle are always equal. So let's draw down all these points in a matching line. So the shape that we would get is a dodecagon. So when we draw down the dodecagon like that, we can obviously understand that the 2 points are the first point and the 6th point. And since this is a regular dodecagon, that should be the symmetrical axis of the dodecagon. Like, let me just demonstrate it to you guys from a simple figure. So apparently I placed the figure a little bit to the center so I could show you the dodecagon. So basically, if we take this point as the first point, we can say 2, 3, 4, 5, 6. And then we can go to the 7th point. First I said it was the 6th point, but it was my bad. It was the 7th point. So when we join those 2 together, that line should be symmetrical. So this can be proven by diagonal formulas and through area formulas. And because this is a regular dodecahedron, we can obviously understand that. So we are going to put this shape back where it belongs with the dodecahedron. So since we got that idea, we obviously know that this is the diameter of this circle. So let's highlight that so it'll be much more visible. Okay, so I hope this is clear enough for you guys. So just make it a little bit more straight. So just give me a sec. Okay, so I hope it's visible for you. So now what I'm gonna do is this simple statement proving. So basically, I know that this side is a common side to these two triangles right here, which are the two triangles that are touching each other where the common line is the diameter. You can see them in the center right here. So basically, in this figure, since these two sides right here in the sides that are included in the dodecahedron are supposed to be equal to each other, and this side is common to both of the triangles, so that should be equal as well. And if I draw another line right like this, we can obviously say that this is an isosceles triangle because these two sides are equal. And we know that this and this makes the diameter of the circle. And since the distance is equal between these 2 points, we can obviously determine that this is an isosceles triangle where the diameter of this particular circle represents the symmetrical axis of that isosceles triangle. So hope that made sense. If you didn't understand it, drop it down in the comment section and I'll do a personalized explanation just for you. And now, since we know that, we can obviously say that these two angles are equal too. And then, since these two sides should be equal because of the same property, we can obviously determine that these two angles are equal, and these two angles are equal to each other as well. So which means the final total angle should be equal to each other too. Okay, so since we know that, we can apply that proving to all of these corresponding angles. We can draw those pairs like this, and I'll show you the math problem again after I draw every single one of them. Okay, so since we don't have enough time left, I'm just gonna say that all these angles are equal to each other correspondingly. I'll just draw a few of them for you guys. So now I hope you can see this. So now in this way, all these corresponding angles are said to be equal. So because of this, we have two triangles and we have two angles proven as equal to each other and one side said to be equal to each other. So which means we can prove that each of those corresponding triangles that we just discussed are congruent to each other. So which means if this is x, this is x, and if this is y, this should be y, and if this is a z, this is a z, and this is a, and then lastly this is b. Okay, so now based on that, we can create the expression of the area of the circle as 2 times x plus y plus z plus a plus b. So now let's just write down this equation in typed form for the clarity and for the convenience of yours. Now this right here is an expression for the area of the circle. Sorry, this is supposed to be z. So, okay, so now we have an expression for the area of the circle. So if we evaluate the area can be expressed as, the shaded area can be expressed as x plus y plus z plus a plus b. So in order to find the fraction, we need to divide this entire thing that total area, shaded one, by the total area. So we had to divide x plus y plus z plus a plus b by this area, which is given as a complex value right here. So let's rewrite the down in a clearer format. So now we created an expression for the fraction of the shaded area. So now we can see this x, y, z, a, b are common to both of the numerator and the denominator, so we can cancel those out. And at the end, what will be remaining as the solution is half. So just like that, we found the area shaded in the first circle, which is a half of the area of the entire circle. So let's just increase the font size of it a little bit so it'll be much more visible for you guys. Okay, back to the problem. So since we're done with this, now as you can see, we have taken almost 11 minutes to discuss this problem. So if we just solve this, we would take approximately 5 to 6 minutes to solve this problem. But as you can see, when we discuss it, we take nearly 11 minutes. So that's why I told you that this problem series is gonna take more than an hour in my opinion. So now we're gonna move on to the next problem. So this was the second figure that we had. Oh, sorry, it's halfway. So here's the complete figure. So now what you have to understand is we have to use the same concepts that we used in the previous circle. That's the knowledge that they're expecting us to see in this problem. So here's the flaw. So now if we take these two corresponding triangles right here, let's take these triangles named as y and z. So y and y, the shaded y and the unshaded y. So if we take these 2 points of both of those triangles, right, these 2 points right here, the number of points in between them is 3. And if we highlight the 2 other points, it increases by 2, which is 5. So, which means that there's always an odd number of points in between. And in those scenarios, the length of those 2 lines should be definitely equal. So that is a really helpful clue to solve this problem. So, which means now if we take these 2 points and these 2 points right here, so now if we draw 2 lines like this to the very center line, which is, it'll be this one right here, this handy line that you can see here right now. So basically this is the central line right here. So when we draw it, you can obviously see how the equality doesn't apply. So that's why we need to have an odd number of dots for this process. So now when we draw it like this, you can see that those 2 lines have equal length. You can see it from the eye level as well, and it's not just accurate from the eye level, it's 100% accurate. So let me just show you how to solve this problem. So basically, now we know that this entire thing is the diameter of the entire circle because we can see there are 5 points in between, right? So because of that, this should be the 7th point, and this is the first point. If we take this as 1, this will be 7. That's what I was explaining. So that means that that line should be the diameter of the circle. So, which means these 2 lines right here should be equal. The same goes to these 2 lines. And the same happens to these 2 angles because those 2 angles are vertically opposite. And 2 vertically opposite angles are said to be equal. So because of that, we can prove that these 2 triangles are congruent. So I'm going to name those 2 areas as X and X. So that looked a bit helpful to solve this problem, but still we're not done yet, okay? So now what I'm going to show you guys, yeah, you guys will be surprised to see this. So you can see that these two lines should be equal to these two lines correspondingly. And this line right here, the imaginary line that I'm about to draw right now, should be equal to each other too, right? Because both of these 2 points are 2 neighboring points, and these 2 points are also 2 neighboring points. So when we join those together, they are said to have equal distance. So that means those 2 lines should be equal. And based on that, based on the SSS congruence theorem, which means if all the 3 sides are correspondingly equal in 2 particular triangles, those two triangles are congruent. So that triangle is also X. It's technically not a triangle, it's a segment. So that segment is congruent to other 2 as well. So now we are moving on to the next part of this. So basically, now what you have to notice is this segment right here, the huge one. Okay, so this looks a lot of confusing in this perspective. So now I'm going to blow your mind by proving this statement that I'm just about to say. So you know that the figure that I just generated in this first problem, this figure right here, it is not clearly visible to you guys, but you might have remembered that I drew a figure like that, a figure which was a dodecahedron. Sorry, it was a dodecagon. So in the dodecagon, there are 12 points with 12 distances separating all of those 12 points, all those 12 vertices. So now, which means in a quarter, there should be 3 distances with 4 vertices in every quarter. So do you notice that same property in here? So I guess we just found out that this is exactly a quarter of this circle. So let's assume the area of the entire circle. Let's take it as A sub C, where I'm going to state that that is A. So this is a quarter of A, so it'll be like this. So now if we can find X in terms of A, that will be the most helpful thing that we can do to this problem in order to get the answer. So let's think about that for a little while. Okay, I think we got the concept now. So as you can see, there are 2 points right here, and the distances between them is 1. Let's name that as a unit. So all of these have a 1 unit distance. So now if we take these 3 distances right here, there are 3. So the distance is 3 units. So in each quarter, there are 3 units. So when we combine these 3 x's, there are 3 units together. So which means when we combine all of those x's, that is going to be a quarter of the circle as well. So the final shaded area will be a quarter plus a quarter, which is going to be a half, right? So based on that, we can obviously conclude that this shaded part of the circle is half of the total circle. So now we're moving on to the third problem. Okay, that's also halfway. Come on. Okay, let me just put that back to you. Okay. So, we have this problem right now, which looks pretty confusing to me, actually. So, what I'm going to do is I'm going to use the same concept that we used to solve the problem number 2, where I named the distances between each 2 points as 1. So in this case, I can join these 5 points. So then it'll be 4 right here. So it'll be 4. Now I know that this is the diameter of the circle. So basically for now, I have no idea about what to do to find the length of the diameter. So I'm going to name it as 2r because I have a feeling that naming it d would be a little bit confusing because it is just one variable. And now since this has a coefficient, we might be able to factorize at some point if we have to solve an equation. So let's keep that in our mind. And now let's move on to our problem back again. So the reason I'm going to say this as a right angle triangle will blow your mind. So basically, first I had to prove that this is the diameter of the circle. So as I mentioned before, if there are 5 points in between 2 points that we are currently discussing, if we join those 2 points that we're discussing, it'll be the diameter of the circle. So now these 2 points are the points that we're discussing. So there are 5 points in between. This is the diameter. And according to circle theorems, if we take a circle and then we draw the diameter, and then we draw 2 chords such as they meet at a 1 point on the circle, we form a right triangle where the right angle is right here. So which means this is a right angle. So which means it's a right triangle. Okay. But still we cannot find any clue for our solution. So I'm gonna go to another perspective. So first of all, another thing that we have to notice is that since the number of points are even in a dodecagon, we can if we join all of these points right here, these 2 points and this point and this squared highlighted point and this and the other circle and square highlighted point, triangle to triangle point, and the heart to heart point. So those points that I just drew for you guys join lines, right? So those lines are parallel to each other. So which means we can say that so we can obviously say that these 2 lines are parallel to each other. Great. So now what can we do? Okay, I think I got one secret thing that we can do here. So I'm going to name this part as 1. And this length should be 1 too. So I can draw another right triangle where the hypotenuse is 1. And these 2 lengths right here are equal. So the perpendicular height and this perpendicular height are equal, right? So, and since this is the dodecagon, these two lines that I just marked. Let me just remark that for you. These 2 lines are said to be equidistant, which means their lengths are equal. So the length of all these 4 lines should be equal to each other. So which means if I divide 1 by the square root of 2, we get the length of one side. So it's 1 root 2. Okay, but I'm not saying we're done yet, okay? We are not done. Okay, so let's see what we can do here. So when we add 1 root 2 and 1 root 2, what is the answer? It's actually the square root of 2. So we know that the distance between these 2 points right here is definitely greater than the square root of 2. Okay, so I had to be honest here. This problem is the hardest one yet. So let me just think of it a little bit more. Okay, guys, so I think I found a new approach for this problem, so we're gonna take that. So basically, because of the same rule that we discussed about about the parallel lines in this dotting again, we can say that these two lines are parallel to each other. And these two lines are parallel to each other in a different perspective. So we need to mark that first of all, because that is going to be vital for this problem in the future. Okay, but still this problem doesn't give any type of sensation idea to me. What can we do here exactly is kind of simple actually. So first of all, I'm going to draw this point right here where there are 2 points in between, okay? So this point is going to be, this line is going to be a line of the same length. So this line should be, this shape right here should be right angled because we drew the triangle from the diameter. So now what I'm going to do, might not be the best thing that you could have done, but I think it might be a good solution to this problem. So what I'm going to do is I'm going to draw this line right here first of all. This line right here. So basically, this line, we're going to call it R because this is the radius of the circle, obviously. So that side is R. This side should be R too because we drew it from the center, right? So we know that these two lines are supposed to be perpendicular, so yeah, it'll be R, R, R in all of these three lines. So now we can find the length of this side as R times the square root of 2. And why did I say that it was R times the square root of 2? If we have a right triangle where the legs are A, this will be A times square root of 2. So that's one simple theorem that you can easily remember. So now, since we know that length, I think it might be very helpful, like really, really helpful to solve this problem. So let's keep that length in our mind. Okay, so still, I do not get how to solve this problem. So I'm trying to take that the approach that we took before back to this problem. So now R times square root of 2 has 2 points in between that line. So I'm gonna draw the same point like that in through our other pair of parallel lines like this. Okay, so now I'm gonna draw a line perpendicular to these showing the perpendicular gap between those two parallel lines. So now I have a right triangle simply. So based on our previous calculations, we know that this area right here is, this length right here is 1 times the square root of 2. So we might need to keep that in mind because that's going to be crucial in order to solve this problem. So we might have like no idea about how to find, so we know that this length is also 1 times the square root of 2. So we can take 1 times square root of 2 whole squared plus, we were in a confusion about this length, right? So I'm going to name it as x. This length right here, this to this. So I'm going to name that as x. So it'll be 1 divided by the square root of 2 whole thing squared plus x plus 1 over root 2 whole square. is equals to r root 2. Okay, so then I am going to find the value for x. So first, to make things a little bit more simple, I'm going to put a value for r, and it's going to be a very reasonable value. So if we analyze this entire if we analyze this entire triangle, at the first glance, yeah, you can't see it, but we can see that the arc length of a quarter is nearly a 4. So 2 pi r divided by 4, like pi r half, should be approximately 4. So I'm going to say pi r is 8, and then I'm going to take an approximation of like the radius is like 2 point something. So I'm going to keep that approximation in mind. Just wait till you see the big reaction. So I'm going to solve this equation right now. Okay, change my mind. So I'm not going to take minus r root 2 to the central part. I'm going to take it to the edge part. So now since we have a quadratic equation, I'm going to determine a, b, and c based on quadratic equation form. So now we're going to simplify the equation using the quadratic formula. Now I can cancel out both of these 2's right here. Okay guys, after a lot of simplification, a lot of thinking, I figured out math was pointless in this case. You gotta use logic. Okay, let me show you how I'm using my logic here. So first we know that this is the diameter. And we know that this line right here has one more point in between these 2 points. And when we consider these 2 points right here, they have the same property. So basically what we can do is we can take this part as x, and then we can name this part as x. And now we have this remaining part. Now if we find the area of this part, and if we add it to the area of this triangle MX, it will be half of the circle, right? So now if I name this area as y. Okay, so I'm going to name that area as y. And this is x. This blue area is x. So now here we can see that there are 3 points right here. These 3 points. And so does this shape from here to here. So which means those 2 areas are equal to each other, so you can take this whole area as y. So y plus the area of the triangle plus x, I said it was half, so which means this is also a half of the entire circle. So now, as you can see, most of these shapes are actually half. So I think this might be a clue for us. So let's just try to prove that every single shape's area is half. Okay. So now let's do the same type of method here. Yeah, let's try to do it. So first of all, here what I'm going to notice is that this, now if we take these two lines right here, now these two lines are starting at a common point. And we can see that there is a distance of 3 points right there. And where this point to this central point creates the diameter of the circle. So which means these two lines should be equal, right? So basically, because of that statement, we can prove that these two lines are equal to each other as well. I'm talking about this point and this, okay? So now those are equal in a separate way.